be your video lesson for 3.2, differentiability. This section talks about what makes a function able to be able to take the derivative. And you'll see some functions have certain places where you can't take the derivative and then other places where you can take a derivative. So we have this statement here: a function will not have a derivative at a point where the slope of the secant line fails to approach a limit. So if you do not have a limit with that secant line, then you're not going to have a derivative. So there are 4 different places where we can't take the derivative of a function. These are in your book on page 111. I'm going to scroll a little bit here. A little bit extra space so you can see these. So you have a corner. Corner is going to be a sharp turn. Typically this happens with absolute value type functions. You have a cusp. Cusp you're going to have anytime you're taking the absolute value of maybe something that's cubed. It almost looks like if you were drawing a seagull as a stick figure. That's kind of what you're going to think about with the cusp. Cusp and corner, sometimes it's easy to get those two confused because sometimes you have a cusp on one side and then like a straight edge on the other. So that's going to be a judgment call whenever that one comes up. Vertical tangent. This happens in the cube root function. Anywhere, if you draw a tangent line, it is a complete vertical, then you can't take the derivative there because the derivative is undefined. The derivative is slope, and slope is undefined for vertical lines. And then, of course, discontinuity. So you have your jumps, you have your oscillations, you have your removable discontinuities, you have your infinite discontinuities, so we can't take the derivative of those things. So we have example 1, find all the points in the domain of the function where f is not differentiable. So first you want to think about what the domain of the function would be. This is an absolute value, and the domain of an absolute value is negative infinity to infinity. So basically any possible number where I would not have a derivative is going to be part of the domain. So you do want to think about that because there are certain functions, especially like square roots and things, where you have a bunch of numbers where there's no derivatives, but they're not in the domain, so you don't have to state those. So if we were to graph this, this is an absolute value function opening up with a vertex at 2, 3. We're going to be looking like that. And so it looks like we have a point where we cannot take the derivative at the vertex value. This is actually a corner, and that occurs at x equals 2. So the only place where this is not differentiable is at x equals 2. It's differentiable for all values less than 2 and for all values greater than 2, but it is not differentiable at 2 because that is the actual corner x value. Here's another concept. We're not going to do a whole lot with this, but it is an interesting application in calculus. So locally linear. Basically any function that is continuous, whenever you zoom in on it, it is going to get very close to equaling the tangent line. So you have at A, so at some point A, a function is going to closely resemble its tangent line whenever you zoom in on it. So if you zoom in far enough, everything is going to look like a line as long as it's continuous. So just that is something that does happen. It's one of the reasons why we use limits whenever we're looking for slopes. This is an alternate calculation for limits. So your calculator does not perform the shortcuts that we're actually going to talk about in 3.3. It actually does this calculation and comes to a result. So you have f prime, remember that means derivative, is equal to f of a plus h minus f of a minus h all over 2 times h. So h is typically going to be some type of small number, like, for example, 0.001. And your book will tell you which number you're supposed to use for these types of situations, but 0.001 is always a safe value. So if a was 4, I would find f of 4.001 minus f of 3.999. So you're going on each side of 4, just a tiny bit greater, just a tiny bit less, and then you would divide by double each. And the value that you get there, this ender, this is the numerical derivative. Numerical derivative is what we call ender. And there is something on your calculator to find that, and I'll actually show you that on the next slide. And notice this one, it tells us which h to use here. So we want to compute ender of x to the third and 2. So x to the third is our function. 2 is the x value. That's the numerical derivative of x cubed at x equals 2. And it says to use h is equal to 0.001. So my ender of x to the third and 2 would be equal to, I would be looking at f of 2.001 minus f of 1.999, and then divided by 0.002. So now I would actually plug in. So I'm going to plug these numbers in for my x value. So I have 2.001 to the third power minus 1.999 to the third power, all over 0.002. So if you do that arithmetic and simplify, you end up with 12.123450 and a 1. So basically, that's going to be 12. It's a safe bet to say that this function has a derivative of 12 at the value of x equals 2. So I do want to show you this on a calculator so you can see how that works. And sometimes your calculator will round these types of situations, but usually they won't. So here's your calculator screen. To get to the derivative, you want to press the math key. And then you're going to go down to option number 8. It says nderiv instead of ender on here, but it is the same thing. If you're using one of the black calculators, you will have to do a little bit of programming with that. As in, it's not going to be as easy as the fill in the boxes like I have on this one. So notice this one, it says ddx of something, well, dd something of something, and then you have something equals something else. So the first thing you want to fill in is your variable, and that's going to be x. Notice whatever you put in this bottom box here, the box over here on the right gets filled in with that same letter. So that just means that is the variable in your function. Now we put the equation, which is going to be x to the third. Maybe if we can get that to and then I want to come out here and I want to fill in the number that I want to find the derivative at. So in this particular question, we were looking at 2. And you can see here they do the calculation and they got the same exact thing that we did working through by hand. So again, this is the formula that the calculator uses. If you have a black calculator instead of one of the newer TI-84 Plus calculators, in order to do this, it's going to say nderiv, and then it's going to open a parenthesis. So after that parenthesis, you are going to type in the equation, then use the comma. You can see the comma key is right here beside the left parenthesis, so you would use a comma to separate. So you always type in the function, then you type in the variable, put another comma, and then you're going to type in the value. And it is important that you put all 3 of those things in there because the black TI-83 Plus calculators are counting on this information in each of these spots in order to pull it into the algorithm that they use to solve. So this will give you the same answers up here. It's just that you have to know the programming aspect of it. So next, compute ender the numerical derivative of the absolute value of x at x equals 0. This may or may not turn out a certain way on your, if you do this on your calculator. If we look at it by hand though, you can kind of see what's happening. And this should kind of be an indication, or it should be tipping some alarm bells here. So, absolute value of x. Sorry, it's a little bit crooked there. It's going to look like that. Well, 0 is a corner. There's a corner at 0. So, really, when you have something like this, you should be thinking, oh wait, I can't take the derivative there because we can't take the derivative of the corner. But if we look at what's going on, if we set this up, we have n of the absolute value of x, and 0. So that's going to be f of 0 plus 0.001 minus f of 0 minus 0.001 all over 0.002. So this would be the absolute value of 0.001 minus the absolute value of negative 0.001 all over 0.002. Well, your top is going to equal 0. And so it looks like you should get 0 as an answer here. But we know that there's a corner here, which means we can't take the derivative. So if we try this on the calculator, just to see what happens, because I think the newer calculators handle this better than the previous ones did. So I'm going to do math 8. Variable is x. My function is the absolute value of x. And I'm evaluating this at x equals 0. And you can see here it does give me an answer. It gives me 0. But we know 0 is not the solution. The solution is there is no derivative at 0. This just further enforces the point that you need to know where you can and cannot take a derivative. You can't rely on your technology to give you correct answers, such as not differentiable. So you really need to make sure that you're careful with that, because truly the derivative here does not exist. Okay, now we are going to use ender and deriv to graph. So we have f of x equals the natural log of x. And I think I'm going to do this mainly on the graphic calculator. I might copy some stuff over here so we can work through this. And we're going to try to guess what the function is that is f prime. So if I go to my calculator, this is the whole reason why my y2 up here is d dx of y1, and I have x equals x, and you'll see that in a minute. So natural log of x is going to be my function. And I'm actually going to turn that function off because I don't want to graph it. But I do want to graph the derivative. So to type this in, the way that I did here, you would do your math 8. So I'll clear this out so you can see how to go through that. I'm going to do math, and then number 8. My variable is x. Now this is typically where you would write an equation. To save some time, you can put something in here so that it is always calling on the same y entry to take the derivative. And that's one of the reasons why I have it sorted. So if you click on this VARS key, which I think stands for variables, and if you go over to y variables, select number 1, function, and then it'll let you select any of the y entries. And I want to select number 1, which means anytime I'm graphing a derivative, I'm always going to be graphing the derivative of whatever is in that first entry. And I want to graph it for all of the x's, not just at a particular number. So I'm going to let x equal x. And then we'll do that. Okay. Let's try that again. Natural log y1 x equals x. I'm not sure why that messed up. It should not have. So I'm not really sure why that is not letting me reference. Yeah, so why not? I'm not really sure why that is not working. Unless I'm not doing it. Figure that out and try using. Well, I'm just going to try typing it in here. I'll have to have an answer for you later on as to why that is not working the way it's supposed to. Let me try it. Yeah. Yeah. I'm going to get back to you with an answer on this. I'm actually going to stop the video at this point, and then hopefully I can backtrack and figure out what is going on.